Okay, good morning, ladies and gentlemen. Welcome to the International Visiting Lecture today with National University Odesa Law Academy from Ukraine. Welcome to the Honorable Mr. Serhii Manakov as Associate Professor, Candidate of Technical Science Ph.D. And for the topic today is Fundamental of Computer Architecture. And for today's session is being live streamed on the Universitas STEKOM YouTube channel. And now I will read our agenda this afternoon. First, we will start class presentation delivered by Mr. Serhii and continue with the Q&A session. In the next session, we have time for documentation and last time is closing. Yeah, let's begin. We will start class presentation delivered by Mr. Serhii. The time is yours. Thank you.
Thank you. Let me share my screen. So let me introduce today's topic. Let's speak about fundamentals of computer architecture, from logic gates to modern processors. What we will cover today. First, digital foundations and logic operators. Then building blocks from transistors to electronic digital components. Then the core computer architecture concepts, performance optimization techniques, and modern processor architectures. And of course, we'll try to understand why it may be important to know these fundamentals for coding tasks, for example. So we have a computer. It is quite a smart device, but it understands only two numbers, zeros and ones, because its native language is binary number systems. So let's remind briefly this binary system. In the binary number system, any number can be represented as a sum of powers of two. So any binary number is just a sum of some powers of number two. Each power of 2 is multiplied by some coefficient that corresponds to the current digit. For example, we have a decimal number 21 here, and we need to translate it to binary. We have to imagine the so-called digit grid, it may be called, because just imagine these powers of 2 beginning from the right to the left. Here we have 2 power 0, then 2 power 1, 2 power 2, and so on. These powers of 2 just correspond to simple numbers from 1, 2, 4, 8, 16, 32, 40, 64, and so on. Each step multiplies our number by 2. So this is the grid of binary digits that we have imagined or write down. So we have 21. And we can understand that it consists of a sum of such powers of 2, like 2 power 4 plus 2 power 2 plus 2 power 0. That is 16 plus 4 plus 1. So we have these powers of 2, and that means that these positions that are called digits, binary digits, that have something in our sum, they became ones, and the absent powers of 2 became zeros. So we have this binary notation 1, 0, 1, 0, 1, or 21. So we can now translate a simple decimal numbers into binary, just using our imagination, or maybe writing down this so-called grid of binary digits. By the way, we can use any number system with any radix, not only radix 10 or radix 2, just any radix, using this simple formula with powers of our radix multiplied by coefficients. The binary system is not only a system that is used in computer science, also octal and hexadecimal notations are widely used. Why? We can see from this table that if we write down 16 decimal numbers from 0 to 15, then next column is its binary representation. We can notice that for storing 16 different numbers or 16 different combinations of numbers and zeros, we just have to use 4 digits. It can be seen from here because only 4 powers of 2 from 0 to 3 correspond to 16 combinations, different combinations. So, and 0 is 4 zeros, and 15, the largest number here, is 4 ones. And then there's also an octal system. It is not so widely used as hexadecimal. Hexadecimal is more important notation, and it is used, as you can know, for example, for writing down the colors, the RGB colors in HTML web pages. And also it is used historically for writing down the addresses, the memory addresses. Why it is used in computer science, this hexadecimal notation? Because it is more close to native binary system of a computer than the decimal system. The radix is 16. And 16 is a power of 2. It is 2 power 4. So it is closer to computer. And we know that, for example, number 15 is F. So it was the alphabet of a computer. Now let's overview some basic operations like logical operations and arithmetic operations over binary data. So we distinguish 3 or maybe 4 basic logic functions. It is these are not, and, or, and XOR or exclusive OR. Let's start from not. It has a meaning of inversion. 0 becomes 1 and 1 becomes 0. And it can be written down in a programming language like this. Then 2 basic and more important operations, and OR. Here it is important to understand the meaning of and OR. I think that it is very nice to think that AND has the meaning of logical multiplication, and OR has the meaning of logical addition. Let's see. So and this is, as you know, a truth table, so-called truth table. 0 multiplied, logical multiplied by 0 gives 0. 0 multiplied by 1, of course, is 0, and here also and only 1 multiplied by 1 gives 1 in result. So this is why AND has the meaning of logical multiplication. And it has such a sign, an ampersand. Next operation is OR. It has the meaning of logical addition. See, 0 plus 0, or we can say nothing plus nothing gives nothing. 0 plus 1, nothing plus something is something, is 1. The same for 1 plus 0, and something plus something is something. 1 plus 1 is not 2, but 1, because it's logical addition. It's OR operation. And the fourth operation, it's not quite the basic operation. It can be constructed using previous 3, but it's also widely used. It is exclusive OR, or XOR, or EOR. It is called. Here you don't have to memorize this truth table. It is more important to understand the meaning. The meaning is that in the result we will have once only when two operands, input operands, differ. For example, 0 and 0 with 1 is 0, and 1 with 0 is 1, because they differ. And 0 with 0 and 1 with 1 makes 0. They are equal. Next, we will see where we can use these operations. But first, let's consider binary arithmetic or operations. The basic arithmetic operation is addition. By the way, subtraction is performed also using addition. We'll see how. And there's a question how to write down negative numbers in binary, or how to store the minus sign. For this sign, people decided to use the most significant bit. It's just the left bit. It will store the sign. If it is 0, it is plus. If it is 1, it is minus. And there's a special form, special notation for binary numbers that is called 2's complement. This 2's complement form is used for storing and operating with negative binary numbers. And this gives us the ability to perform the subtraction just using the addition. We will see in the next screen, but first let's see how to convert into 2's complement. For example, we have to write down -5 in binary. At first, we have to consider how many bits do we have for this operation. Because in a real CPU, we have its memory, its random access memory, and each memory cell has a specific size in bits. For example, we have 8-bit memory cells. So we have 8 digits for our -5. First step, to get 2's complement, we just have to write down our 5 in 8 bits. We already know that why it is 1, 0, 1, because 2 power 0 is 1, and 2 power 2 is 4. 4 plus 1 makes 5. Okay, next simple step, we just have to invert this 5 to change zeros to ones and ones to zeros. And in this step, we already have our sign byte. It is sign bit, sorry. It is 1 and it's minus. And final simple step is adding 1, and then we get our negative -5 number in a 2's complement notation. So this number is a 2's complement for 5, for -5. And now we can see the next example where we have to perform a subtraction. 7 minus 5. We can write down it without subtraction, because 7 minus 5 is the same as 7 plus -5. Then we will perform a simple arithmetic addition in a row. Let's write down our operands, 7 and -5 in a column, sorry. And let's add each binary digit. And here is the next trick that we should remember how to perform this addition. Here we have this special situation. We have to add 1 plus 1. We know that it must be 2, but 2 in binary system is 1 0, like 10, but it's 1 0. What we have to do? We have to write first the less significant bit. The less significant bit is always from the right side. It is 0. And the 1 is being transferred to the left, to the next digit. So in the next digit, we have 1 plus 1 and plus another 1 from the previous step. So we have even 3 ones here. We know that 3 ones makes 3, but 3 in binary is 1 1. So we just write down our less significant bit from 1 1. There is 1 here, and we also transfer the next one to the left. So in this position, we have 0 plus 1 and plus previous 1. So we have 2 ones. It is 1 0. Here is the 0. 1 is transferred, and so on. And in the result, we will receive such a number, which can, as you can see, has 9 digits. We have an overflow situation because our physical memory cell can only store 8 numbers, as we decided. And this, from the left, is destroyed. And it has not, it doesn't have any meaning. So we receive the result. It is 2. And I think it is correct. So this is how the subtraction is performed using the addition and 2's complement form of negative binary numbers. With these 3 simple steps for conversion into 2's complement. By the way, if we should have another example, for example, vice versa, 5 minus 7, yes, then we should receive -2 in the result. And this is the sign bit. Now it's 0 because it's positive number. And if we should receive the negative result, this position, this sign bit will be 1. And that means that our result would be in 2's complement form. And if it would have minus here, then we should perform these operations to convert it back from 2's complement in a direct, in a binary form. Just all these steps, vice versa. Subtracting 1, inversion is the same, and we will receive our direct form of a result with a minus. Okay, I hope you understand it now. Then we will see why it is useful to know these logical operations. Maybe it is more simple than these arithmetic operations with subtracting. Let's consider so-called bit masking operations. For example, we have a task. We have a binary number with 8 bits, and we have to extract bits from 4th to 7th. That means we have to extract the left part of these 8 bits. Here we can use a so-called mask. It is also a binary number with ones and zeros in proper digits. For our first 4 bits, let's place ones in these positions with zeros in the rest. And let's perform the logical AND operation with our initial value and our mask. With this AND operation, that is, as you know, logical multiplication. Zeros in the mask are multiplied by the values and result in zeros. And only the bits that contain ones in the mask will repeat our initial bits. So now we get this for bits from 4 to 7, and we have zeros in the rest. We just don't need them. This is the masking operation with AND. Of course, we can take OR operation and XOR operation. With OR operation, we can set specified bits to ones. Why? So, because OR operation has the meaning of logical addition. If in the mask we have ones, they would be added to zeros, and they will make all zeros ones. And at last, for the task of inverting the specified bits, we can use XOR operation, the exclusive OR. Because if we look at the truth table, we see, just imagine that first operand, these 4 bits, is our initial value. The second operand, B, also 4 bits, is a mask, and the output is the result. Let's apply this mask with XOR to our A number. You see that bits in the mask that contain ones, they just invert our initial bits. This 0 became 1, and here this 1 becomes 0. So XOR, while using in a mask, has the meaning of inversion, can be used for inverting specified bits. So these are masking operations, and you may ask, why should we need to know it? Just imagine you have an Arduino board and you want to control 8 LEDs, 8 little lamps, and you have 8-bit physical port with 8 physical pins with each LED on each pin. This logical 1 will turn your LED on, and this 0 will turn it off. So using masking operations with logical functions, you can easily control your LEDs. So this is an example of practical using. Now let's move next. And let's briefly consider the building hierarchy of the computer digital devices. In the lower level, we have transistors, diodes, and transistors. As you know, modern CPUs or modern digital devices, chips, they have millions transistors on board. Next level is logic gates. It's our logical functions, not AND or and XOR. They all are built using these transistors and diodes as main components. On the next level, we have so-called flip-flops. In our countries, we call flip-flops as triggers. So these flip-flops are built on logical elements. And on the next level, these different types of flip-flops they are used to build more complex components like counters, adders with subtractors, multipliers, maybe the coders, decoders, and other basic components of any computer system. Next, let's consider the computer architecture basics. Every computer has three main components. This is the CPU or central processing unit, the memory subsystem, and input-output subsystem. We see that CPU has such main elements like control unit as a some digital device, the arithmetic logic unit. This is the part of CPU then can count, and that can use our logical operations also. And we have the simple memory cells, the private memory cells of our CPU. They are called the registers. This is not RAM, this is not ROM, they are registers, and each register has its own name. For example, A register for accumulator, R1, R2, R3, and so on for data registers. Each is a memory cell inside the CPU, and registers are the fastest memory unit. Then we have the memory subsystem with RAM, with cache, memory, and storage devices like HDDs, SSDs, and flash cards. And the last is the input-output system to communicate with the real-world devices and with the human. For this, we have ports like serial and parallel ports. For example, USB is a universal serial bus, and it is a serial port. Of course, we may have some keyboards, some display, some network devices, etc. And we can represent it as a simple scheme, the generalized diagram of a computer with CPU, memory, and input-output devices. We see that all they are connected via so-called buses. And we consider the three types of buses that are the data bus, the address bus, and the control bus. For example, you are buying your new computer. At first, you may choose a processor type model of your processor. You go to the shop and you see that all modern CPUs are so-called 64-bit CPUs. What these 64 bits are? It is simply the wideness of our data bus, because data bus of modern CPUs has 64 bits wide. What does it mean? It means that on each CPU clock tick because CPU has an engine. It is the clock speed, clock frequency generator. As you know, it is measured in gigahertz. Tomorrow, for example, 2 or 3 or 4 gigahertz for our clock speed. Each tick of this clock generator, for each tick, our processor can operate with such a big numbers that have 64 bits. That means that the largest number is 2 power 64. 2 power 64 is the extremely large number. So this is the meaning of our CPU bitness. It is just the data bus. Then we have the address bus because for memory devices, they all consist of memory cells. Each memory cell has its own address. It is a number of its location that represents its location. And which meaning does have the wideness of our address bus? How many bits it uses? You can understand that the more bits has our address bus, then the more memory cells we can address, and the more RAM, for example, we can install in our computer. So this is why it is important to understand the address bus bits. And the control bus, the third bus, it can be imagined like the control lines in our motherboard, for example. Now we see these three basic buses: data bus, address bus, and control bus that connect our main components of our computer. By the way, here we see that 8 and 32 bits for data bus is used in microcontrollers. MCU is microcontroller unit. This is like Arduino, for example, because no, let's speak it in the next. And now let's consider two basic computer architectures. They called as von Neumann and Harvard architectures. The simple meaning, the simple difference. And von Neumann architecture or Princeton architecture uses single memory for storing data and commands. We have we have both our program code and program data, our variables, arrays, and other stuff in a single memory. And this produces so-called bottleneck of this von Neumann architecture. And by the way, it is used in Intel and AMD CPUs. And second type is Harvard architecture that is used in, for example, microcontrollers and mobile chips. Okay, I will answer your questions after after this. Okay, don't forget to ask your question. And for the Harvard architecture, we have a simple difference. Data memory and program memory are different types of memory devices with the different buses, data and address bus for them. Yeah. As I already told, it is used in microcontrollers and mobile chips. What does it give? This gives us parallelism. We can read the instruction what to do and the data with what to do. it in one single CPU tagged CPU clock. Okay. Now, briefly about the main CPU components. At first, we have the fundamental operation cycle that repeats billions of times per second inside the CPU. It is fetch, decode, execute cycle. What is being fetched? These are the instructions, the commands. Then we have to decode our instruction because it is represented in binary in binary form. And it is called as a machine instruction because, as we know, the CPU knows and it understands only ones and zeros, and each instruction looks like a set of one and zeros, and we need to decode it. And after this, we can execute it. This is the fundamental cycle. And as you can see, again, these two architectures in von Neumann architecture, this is about our Intel and AMD processors. We have a bottleneck because we have to fetch instructions and data via same bus, and we have at first to fetch our instruction, and then we have to fetch our data. And in Howard architecture, we can make it in parallel. So inside the processor, we have so-called control unit that orchestrates all operations, decodes the instructions. The ALU, the arithmetic logic unit, it performs arithmetic and logical operations. A set of registers, which are ultra-fast temporary storage cells, and the clock, or clock generator, which synchronizes all operations. It is like a heartbeat of our CPU. So now briefly about the memory hierarchy and the I/O systems. Memory types. We can distinguish volatile and non-volatile memories. Among the volatiles, we have registers, which are the fastest and the smallest ones. Each register can be 1, 2, or 3, or 4, or 8, several bytes. Then we have the cache memory. It is the fastest memory after the registers. It has some layers, for example, layer 1, layer 2, and layer 3, and it is very fast. And it is measured in kilobytes or megabytes. Then we have RAM memory, which is random access memory, and it is our main memory, which is measured in gigabytes. And our storage devices like SSD or flash memory are non-volatile, and they are measured in terabytes. Okay. So the so-called instruction set architecture. Our processor for each specific model of a CPU has its own set of instructions. These instructions are used in assembly language, which is slightly different for each CPU. We can distinguish such instruction types as data movement, arithmetic or logical instructions, and control flow instructions, and other system operations. The key concepts here are the addressing modes, instruction formats, the register sets, and data types. All this is being studied if you want to master the assembler language. Just a few words about it. It is a different topic because why may we have to learn assembler language today? Because we have many beautiful languages of high levels like C++ and many other. You can use assembler language if you want to reach the fastest operation and the less code size. So assembler gives you the maximum speed for your code, and it also gives you the minimum of its compiled size, because the assembler is the closest for the CPU's native language, which is the binary system or the machine codes. So just a last word about assembler. In assembler, we don't use variables. We use registers instead of variables. Okay. There are also such types of architecture that are called RISC and CISC. RISC is reduced instruction set computing, and CISC is complex or complete instruction set computing. The difference: RISC is used in ARM and MCUs like Arduino or ESP32 or STM MCUs. It is simple. It has fixed length instructions. It also has large register set. For example, R0, R1, R2 to R64, R63, many registers. And it has load store architecture. From the other hand, CISC, like complete instruction set computing, it is used in our regular CPUs like Intel or AMD. It is complex and it has variable length instructions. It uses fewer registers set. And it can use memory operation in assembler instructions. So we just have to remember that RISC has many registers and fixed length commands, and is used in mobile or MCUs. Next, briefly about pipelining fundamentals. The assembly line of computing. First, we have to fetch the instruction from the memory. Then we have to decode it. Then we have to execute it. Then we have the memory access, and then we write back the result. Some hazards and solutions about pipelining. Data hazards. Instructions depend on previous results. The solution is forwarding and stalling. Control hazards. Branch instructions change the flow. Solution is branch prediction. What is branching? It is we can consider branching instruction. Vocational is like a go-to operation. We specify the address, where to go, where to continue our code execution, and we move there to that line of code. And for the conditional branching instructions, each of them has its own condition to make the jump, to make the transition. For example, greater or lower is equal to 0 or is not equal to 0, and so on. And for structural hazards, we may have some resource conflicts and we can use resource duplication. And for modern processors, over 19 pipeline efficiency is achieved. Let's see what is about parallelism in computing. We have several types of parallelism. Instruction level, ILP, multiple instructions execute simultaneously. Thread level, TLP, multiple threads on multiple cores execute in parallel and simultaneously. Data level, DLP, same operation on multiple data, which is called SIMD or SIMD. And task level parallelism, which is independent tasks distributed across processors. So again, about memory hierarchy. Registers are fastest and smallest and are located inside the CPU. Each CPU has its own register set. Then the cache. Level 1 cache uses about one CPU cycle to operate. And next levels like L2 and L3 cache use from 10 to 40 cycles. RAM uses even more cycles, and outer storage like HDD is the slowest and the largest memory device. About cache memory. Cache memory is the fastest after the registers. It is located nearest to the CPU, reducing memory access time by 10 to 100 times. And finally, let's speak about modern processor architectures from MCUs to AI accelerators. We can distinguish two basic types of processors. These are microcontrollers or MCUs, microcontroller unit, and regular multi-core CPUs like Intel Core i7 or AMD Ryzen. What is the difference between them? An MCU, for example, it may be the Arduino board, an ASP32 or STM32 chip. They are cheaper than Intel or AMD. They are simpler. They are slower, but each MCU is on crystal computer, which has its own CPU core, its own memory, even its own input-output devices that are integrated on single chip. And also MCU is characterized by lower power consumption and is used for real-time applications, because the word control has the meaning that we want to control some real-time device. For example, in a computer, each device, like the screen, the mouse, the keyboard, and so on, has its own controller, like a manager person that controls this device and can speak with the CPU as like with the boss. So microcontrollers can be used like managers for the computer components. And our regular CPUs, they are, of course, expensive, they are fast, they are complex, they have multi-threading, but they don't have any RAM on chip and any ports, input-output ports. All these devices are on the motherboard. So regular CPU needs the motherboard with memory and ports at least to operate as a computer. Also, we know some special chips like graphics processing unit or GPU or tensor processing unit for deep learning and neural networks. GPU has thousands of simple cores, is optimized for parallel workloads, have simple instruction over multiple data architecture, and has higher memory bandwidth. TPU or NPU, neural processing unit or tensor processing unit, is used especially for AI and ML tasks, is optimized for matrix multiplication, has extremely high throughput and energy efficiency. But it cannot be used for simple visual tasks like a visual CPU, only for its special tasks. And the battle of architectures, the ARM vs x86 or x64. ARM is used in smartphones, tablets, Apple M series devices, Apple, and x86 or x64 is used in desktop PCs, servers, workstations. We see this word RISC in ARM and CISC for x86. The reused instruction set and the complete instruction set. ARM was invented in Britain, and it used the special license because it only sells the documentations, and the manufacturers use it to build their own chips with ARM architecture. On the other hand, x86 has the well-known compatibility for decades of software support. Next, about the performance metrics, clock speed, frequency of operations measured in gigahertz. Higher is faster, but not the only factor. IPC, instructions per cycle, per one cycle, how many instructions are executed, measures efficiency of architecture. By the way, about 20 years ago, it was measured in millions operations per second, millions operations per second. Now it is instruction per cycle per one single cycle. And so overall performance can be imagined like a clock speed multiplied by instructions per cycle and multiplied by the cores number. About some optimization strategies, hardware level optimizations, branch predictions. To get branch, it outcomes to maintain pipeline flow. Speculative execution, execute instructions before knowing if they are needed. And out of order execution, execute instructions when ready, not in program order. So the real-world applications, ARM processors are used in mobile devices. They balance performance and battery life. For data centers, multi-core x86 and ARM servers are used for cloud computing. For AI, ML, GPUs and TPUs for neural network training. For IoT, we use MCUs, microcontrollers, like Arduino. For embedded systems and sensors. For gaming, of course, we need GPUs for real-time rendering. And for autonomous vehicles, we can use specialized processors for sensor fusion, for example. Key takeaways: digital systems built from simple logic gates to complex processors. Instruction set architecture defines the interface between hardware and software. Pipelining and parallelism enable modern performance. Memory hierarchy balances speed and capacity. Different architectures, CISC or ARM x86, suit different needs. And modern systems are specialized processors like GPU, TPU for specific tasks. So understanding computer architecture can help you to write better and faster code. Thank you for your attention. Now we can proceed the discussion. So I can see a few questions. Now let me see. Abdul was asking about how the binary number system helps computers process information more efficiently. As we know, the binary system is the only system that computer can understand for real. Why so? Because it is constructed in the lowest level on transistors and diodes, and that it means that we have logical ones and logical zeros. A logical zero is can be imagined like an 0 voltage, and logical one can be imagined like some voltage about some standardized level, for example, 5 volts, 3.3 volts, or about 1 volts, and so on. So this is the logical one. I hope you understand. So because it is based on digital devices. Next question: what is the main reason that 0 and 1s are used as the only symbols in binary representation? I think it's the same answer. Should computer architecture education focus more on theoretical design or practical implementation using simulations? Yes, interesting question. There are many simulation software. Tomorrow we can use it, for example, to build to model our CPU and MCU circuits. For example, Proteus, how can you spell it, allows us to make a scheme where we can place our MCU like Arduino. We can place some basic components like LEDs, buttons, displays, and so on, and sensors, of course, and to simulate it with the code loaded to our virtual MCU with the real code, and we can simulate it. And the last question here, I'd like to know, how does computer architecture relate to emerging technologies such as artificial intelligence of cloud computing. Has CPU types like GPUs, TPUs, and or NPUs for tensor processor units or neural processor units that can help us with the tasks of artificial intelligence or machine learning. Because they are intended for matrix operations, and our neural networks, they all use these matrix operations to learn our neural networks. Maybe there are more questions. Okay, thank you. I see. How important is it for students to understand low-level concept like instruction cycles or data paths in today's software-driven world? Yes, that's a good question. Thank you. This knowledge is maybe used in deep optimization. For example, if we take cache memory in our Intel Core i7 CPU, if we see the documentation, if we see the manual, we will learn that cache memory of level 1, the fastest cache, is constructed, is built of the blocks which have the size of 32 kilobytes. Then we will know how to get the maximum performance. We will use the data that will be cached, and we will divide it in these blocks of this size of 32 kilobytes. And because we know that it will suit better for caching inside the CPU. It's just one single example.
I guess no one else asking again, sure? Yeah, thank you for
Thank you.
your answer. And before I close this event, for all participants, on your camera, icon of 3 for documentation. In cooperation. Finally, we come to the end of visiting lecture today. We would like to thank you for Professor Serhii for the wonderful information and sharing your knowledge. We hope this information will be beneficial for all participants. At least we have to have more collaboration in the future with National University Odesa Law Academy. The visiting lecture for today and here. Hope to see you soon. Thank you and have a nice day. Thank you so much.
Thank you very much. Wish you good luck to all the students. And it
Yeah, thank
was my
you.
pleasure.